Okay, now it's recording. Okay, the background noise is the kettle boiling. So today we're going to keep going with greedy algorithms. We're going to start off, actually I'm going to close that so it doesn't distract me. We're going to start off with pretty not super hard stuff. So did people, here I'll switch it to where you can vote. Oh, again, the setup is going to be that if you want to ask something or say something, so everybody please have your mics off. But then if you want to ask something or say something, then you can like message or put your hand up or something, and Mojan will handle the class while I'm teaching, and then she can turn, if she thinks I should know something, she can turn her mic on and tell me. Okay? So, I hope, did people go, you can put your hands up now to vote. Oh, that's it, that's neat. How did you do the, okay, you can give yourself pictures, I guess. And so that's the thumbs up picture. Did people go to the tutorials? Yes. Okay. Some people. Good. Okay, people did. So, last week on Wednesday, we saw the this problem of, given a bunch of sorted but unequal lengths lists, figure out how you can merge them optimally. And then we saw that that's actually the problem of constructing an optimal prefix-free code. And so the algorithm we came up with for that is Huffman's algorithm, which is famous for constructing an optimal prefix-free code. Normally, previously when I taught this class, I taught Huffman's algorithm without that nice introduction, and then it's pretty gruesome. But this way, it started off with something not so painful, and then we saw this big famous problem. And then for the tutorial, you saw you start off with the gas station problem, I believe. This problem of, which is actually from the book. So in my version, it talks about gas stations, and in your version, in my edition, which is from the 90s, it talks about gas stations. And in your edition, it talks about somebody trying to rollerblade across Minnesota or something. Okay, so this is quite natural, because you think, how would, if you were trying to drive a certain route and you knew where the gas stations were and you wanted to make as few stops as possible, in real life, what would you do? Well, anybody would do the greedy thing, which is drive as far as you can, but stopping at the last station where you can actually get gas. Unless you're with somebody who is like, oh, we should stop here because maybe the next gas station will be out of gas and then we'll be stuck. But, you know, the obvious thing to do is like, okay, we go as far as we can, but then we refuel at the last stop, at the last possibility we have. And then if you're out driving with somebody and you said, oh, well, maybe we should stop here. And they said, but there's another gas station we can get to. And you said, yeah, but maybe if we stop here, there's a possibility that somehow later this will benefit us. And they'd say, you're crazy. Like, obviously, they would come up with the exchange argument. Well, they might not. They might just ignore you. But they might intuitively come up with the exchange argument and say, what do you mean? How could it possibly be the case that if we stop here, we might be able to make fewer stops? Because if we stop here, anything we would do from now on, we could still do by going that extra step to the next station and filling up there. Then you get this idea that, you know, anything you do from then on, you do the exchange argument. They probably wouldn't say it in terms of, assume that after I steps, your sub-solution after I steps can be extended to an optimal solution. show that after I plus 1 steps, your sub-solution can be extended to an optimal solution S prime. They wouldn't put it that way. But the intuition is fairly clear. This is not that bad. So I don't want you to think, now I don't want you to think that it's super easy. Because people do get this impression. This is one of the reasons I started off with coloring and really hard problems, even for divide and conquer, because people get the impression that divide and conquer and greedy are really simple and easy and you can only use them on sort of low-level problems. And that's not true. For example, I have a reminder to myself written down somewhere to tell you about, well, not actually teach you the simplex algorithm, but for a long time people solved linear programs using an algorithm called simplex. So if you've done combinatorial optimization, most people still use this algorithm, the simplex algorithm, which sort of, you have this polytope in high dimensions, and you walk from vertex to vertex of the polytope trying to optimize. And it's a greedy algorithm. And it's not that simple, and it's not that fast. It can actually take exponential time. So for a long time, people didn't know if linear programming was polynomial time until they came up with a much more complicated algorithm called the ellipsoid method. And now there are other techniques, which I knew at one point, but I had forgotten. So today we're going to start with something that's about the same level as the gas station problem, and then to convince you that this isn't easy, trivial stuff, I'm going to go back to working on hard problems again with greedy algorithms. Sorry for the clap. Okay. We have a few people. Yes, we're recording. Good. And the kettle is boiled, so I can make tea when we get to a break. So the first problem I want to talk about is, it's in the book, it's called fractional knapsack. So imagine that you're going camping, because the weather is amazing right now. Wow, this is so good. So you're filling up a knapsack with food. And you happen to be only taking food that you can cut. Okay? So no jars of pickles. Okay? A single pickle you can cut, but a jar of pickles you cannot cut. Okay? So no, like a water bottle, either you have a water bottle or you do not have a water bottle, but you can't take half a water bottle. Okay, but now we're just considering things like cheese, what else? Can you, like you could cut a loaf of bread, things like, presumably you could cut a chocolate bar if you really wanted to. Be a bit messy, but okay, so stuff you can slice. Right? So now you have your knapsack. And your knapsack has say, I don't know, I forget how much can I carry? I can carry like maybe comfortably? Let's overestimate and say I can carry, on a really good day, let's pretend I could carry 20 kilos. Okay, can you see the board? Maybe. Yes, good, okay. So everything, now you have a chocolate bar, which is 100 grams. You have a loaf of bread, which is, I kilo, don't know if that's true, you have cheese, I like cheese, let's say you have 2 kilos of cheese, and so on. But everything you can cut. Okay, actually let's say, to make this a bit more, let's say that you can have, let's say I'm just carrying 10 kilos. I want to walk quickly. Okay, so everything doesn't just have a weight, it has some value. Okay, wait, am I walking or are you walking? Either way, okay. So it has a value. So let's say this has value, can't spell. Value 12 units. Value 12 units. This has value 6 units. Maybe this is calories. Okay, value 10 units, etc. Okay, so now the question is, you want to fill up the backpack in such a... Ooh, there are questions. Mojan! Mojan! No, okay, there are no questions. Okay, never mind. Mojan, is your mic working?
Yes, it is working.
Okay, good. So, hello. You can also ask questions. If I say something and you think it doesn't make sense, just stop me and let me know. So, you want to fill up the knapsack with stuff. So presumably you have more stuff than will fit in the knapsack, than you can carry. But you want to fill it up, you want to select stuff such that the knapsack, you end up carrying as many units of value as you can. Okay? Is the problem clear? So you're given this long list of things, and you want to select things to put in the knapsack to maximize your value. Okay? Good? Okay. We have fewer people than last week. Boo! It's there again. It's another beautiful day. It's a Monday. I have 27 people. No, okay. Yes. This is fractional. Knapsack. So every item is, I believe the term is fungible. Okay, but let's suppose I only have one chocolate bar. Okay. Only the physical, not the dimensions, the objects themselves. Yes, so we're only going to talk about, it's like a one-dimensional thing. Okay, yes, it's not like, we're not playing Tetris with the chocolate bars. It's just weight, or it could be volume. I mean, if I did this in liters, this would be volume. But yeah, you can cut them and you can also squish them. Okay? So, don't overthink this. What would you do? Yes, if you take the whole 2 kilograms of cheese, you get value 10. If you cut it in half and you take 1 kilogram, you get value 5. Okay? So the value, if you cut an item, the value you get is proportional to the amount that you take. So, what would you do? Okay, but let's say I only have one. Okay, that one. Let's go with that last suggestion. because the thing is, it could be, so let's explore the other suggestions. Okay, let's suppose I only have one chocolate bar. So I would take probably I would take the chocolate bar. But I wouldn't, if I had something, I'm trying to think of what this could. Okay. So let's suppose that on this list there is oh no, sorry, this is going to be 10 kilos. Okay, maybe it doesn't even have to be that giant. How much is, yeah, that would be pretty big. But no, I've seen watermelons that big. In Italy, they get really, in the south of Italy, they're huge. Okay, so let's suppose that I have the option of taking a giant watermelon, which is 10 kilos, and it has value 20. I probably wouldn't, I mean, that could be the most valuable item, but it would completely fill my backpack. So we don't want to just take the most valuable thing, because then I can't take anything else, whereas if I took the cheese, the bread, and the chocolate bar, then it wouldn't even fill my backpack, and I would have value 28. So it's not the most. Now there was another suggestion, actually, but wait, Mojan is
Yes.
okay, but right now there was, yes, so yes, the idea is we want to do value dense. So we're going to take the ratio of the value over the weight, and we're going to, and which is, so the density, and then we're going to take the most dense item. And if we can't take it all, we're going to cut it and take as much of it as we can. Okay? So in this case, maybe it's, so we can take the whole chocolate bar. And then maybe the second most value dense. So what is this density? This is 12 over 0.1 equals 120. Okay. This density is 6 over 1 equals 6. This density is 10 over 2 equals 5. Okay, then maybe what can be my second dense? Well, okay, let's say that I have something here which is, help, what can I take? I forget the name of this second. Mazapan? Okay, so somebody, what's a food that can be cut? Carrots. Let's say that I can take 5 kilos of carrots and they have value, okay, so density, this is density 1, this is 12. Let's say carrots, 5 kilos, and they have to be a higher density than anything else, so they have to be, say, 31. Let's say this is 31. So that way, the value divided by it is a little bit bigger than 6. Okay, and so on and so on. So, does everybody understand how we sort the items? And then it's greedy in that we take it, and we take as much as we can, and if we can't take everything, we cut it, and then we stop because we filled up the knapsack. And if we have space left in the knapsack, then we take the next thing. Okay? So, pretty straightforward. How do we show that this is optimal? Well, so remember, I'm giving you this template how to prove greedy algorithms provide optimal solutions. So, what you start off with. Before we take any steps, we have not messed up, okay? Our empty subsolution can be extended to an optimal solution. So let's suppose, now what does this mean? It means if we have, suppose we're doing some task and some algorithm expert is on the way, right? But the algorithm expert is arriving at noon and we have to sort of keep things running until then. So the idea is, we don't say that they have to follow our algorithm. We just say that we have to not mess up. We have to do things in such a way that when they finally get here, they can take the solution, the sub-solution, which we've got so far, and then they can finish it off in a way that the total solution is optimal. Okay? So they're on the way, but we have to take maybe the first few steps and not mess up. Okay? So that's what it means. Now, before we do anything, we haven't messed up. Because if they arrive and we haven't done anything, then nothing is our fault. Okay? So we just have to be concerned about, okay, when we take a step, do we mess things up? Do we break things irrevocably in such a way that even when they arrive, however good they are, they can't get an optimal solution out of it? Okay? So, before we take any steps, when we have taken 0 steps, our empty subsolution can be extended to an optimal solution, right? Because we haven't done anything that they wouldn't do because we haven't done anything. Okay? Do people see that? No? You could look around and... Yes? Okay. Somebody understands. The thing is, I can't see if people put up their hands when I'm on the chat thing. Okay. So... Suppose that after I steps, our subsolution can be extended to an optimal solution S. Okay? So it's now, okay. Somebody's asking something. Okay, no, just putting their hand up. Okay. Is the camera, yeah, the camera can see pretty much all the whole way. Before, yes, okay. Okay, so it is now 11 something something, oh no, it's 12. Okay, suppose that the algorithm expert is arriving at 12:30 and this, we have to take a step every 5 minutes. So we just have to take 6 steps. And we just have to not mess up in the first 6 steps. Suppose that we manage to do that. So it gets to 12:30 and we haven't messed up. So there exists a way that the algorithm expert can arrive and extend our sub-solution to get an optimal solution. So maybe we didn't do what the algorithm expert would do. Maybe those 6 steps, we did our own thing, but there is still a way they can fix things and still get the same optimal solution, or not the same optimal solution necessarily, but the same value, the same total value in the knapsack that they would get doing their solution from the beginning. Okay? Because there could be multiple optimal solutions. So that's for the first 6 steps. But then the algorithm expert gets stuck in traffic and calls and says, "Oop, I'm going to be 5 more minutes." Okay? And then we think, oh, okay. So now we're going to have to take another step. So the idea is, we show that after I plus 1 steps, is this big enough? Moshe? Big enough?
Yes, it's good.
Okay.
Only one person is saying it's too small.
Oh wait, somebody said it's too small? Oh, okay.
It's not too small.
Full screen option? I don't know. Okay, I can try to write a bit bigger. There exists an optimal solution S prime. So wait. After I plus 1 steps, our subsolution can be to an optimal solution S prime. Now, this means that at 12:30 I can only blow you up so much. Okay, yeah. So is this okay? This is a little bit bigger, these 3 lines.
Yeah, it's okay.
Okay, yes, good. Okay, so this doesn't mean S prime has to be S. Maybe at 12:30, if the algorithm expert arrived, they'd be able, they do the rest of our solution one way, S, but now we do another step and they'll arrive and say, wow, I would never have done that. But don't worry, I can still fix things and get the optimal value in the knapsack. So we can still get, there is an optimal solution. Okay? And usually how this works, you use this optimal substructure. This stuff is in the book, so you just have to, it's pretty much always the same. It's not always easy, but it's pretty much always the same. You have to, the trick is to find how you sort. So at the beginning, do you sort by size? No. Do you sort by value? No. Do you sort by ratio? Yes. This is like, you saw the activity selection on Friday in the tutorials, right? And the TAs said, you know, how do you sort these activities? Do you sort them, do you take the one that has, do you sort them in order of start time, which is a natural thing to do, but wrong? Okay, do you sort them in order by duration, which is another natural thing to do, but also wrong? Or do you sort by shortest duration first? No. Longest duration first? That would be a bit weird. Then finally you get to, okay, do you sort it by deadline? Okay, you went through this? Moshe?
Yes, we did.
Okay, Good. And so you figure out how to